In this video, we'll learn the third kind of conversions, conversion between binary and the octal and hexadecimal systems. So far, we have learned how to convert numbers from the decimal system to other systems and from any other system to the decimal system. So in order for us to convert any number from a system to another, we can use the decimal system as a mediator, and that is by converting the original number to the decimal system and converting the result in decimal to the desired system. But didn't we mention that the octal and hexadecimal systems originally are representations of the binary system? So could there be an easier way to convert numbers using that? This table shows some numbers in the four main systems we learned. Here the radix equals 8, radix equals 2, radix equals 60. Let's focus on the full range of a single octal bit. It exactly matches the full range of 3 binary bits, as here the number needs 4 digits to be represented. And that is due to the fact that 2 to the third equals 8. And if we look at the full range of a single hexadecimal digit, it exactly matches the full range of 4 binary digits. And similarly, that is due to the fact that 2 to the fourth equals 16. That means any single octal digit can be represented using 3 binary bits, and any hexadecimal digit can be represented using 4 binary bits. Let's see how that plays out in an example. Our example here says convert 1001110 binary to the octal and hexadecimal. So here we'll start with the generic approach where the decimal system is a mediator. So we convert the binary number to the decimal and then the result in the decimal system to the octal and hexadecimal system. Then we will utilize what we have just learned in converting the number directly from the binary system to the octal and hexadecimal system. Let's start with the generic approach. So we have a binary number here. Let's convert it to the decimal. 1001110 binary. Let's lay out the position multipliers. 1, 2, 4, 8, 16, 32, and 64. So we have 1 at 64, 1 at 8, 1 at 4, and 1 at 2. So the result is 64 plus 8 plus 4 plus 2. That equals 78 in decimal. So we have done the first part, and then we have to convert 78 decimal to octal and hexadecimal. Let's start with the octal. 78 decimal is a whole number, so we only have to convert the whole number. We have the quotient column here, remainder column here, and then we start our iterations. 78 divided by 8 equals 9 as an integer and 6 as a remainder. So the quotient gets 9 and the remainder gets 6. 9 doesn't equal 0, so we continue. 9 divided by 8 means 1 as an integer and 1 as a remainder. So quotient takes 1, remainder takes 1 as well. And then 1 divided by 8 equals 0 integer and 1 as a remainder. The 0 as an integer here means we stop. And the LSB here is 6. So 78 in decimal is equivalent to 116 in octal. Alright, and then let's convert 78 decimal to the hexadecimal system. Same approach applies here. Quotient column, remainder column. 78 divided by 16. That is 4 as an integer and 14 as a remainder. 14 is equivalent to E in the hexadecimal system. So we have 4 in the quotient column and E in the remainder column. 4 doesn't equal 0, so we continue. 4 divided by 16, that is 0 as an integer, 4 as a remainder. So here we have 0 in the quotient column, 4 in the remainder column. We have reached 0, so we stop. LSB is E. So 78 decimal is equivalent to 4E in the hexadecimal system. That means we are done with the generic approach. Now let's see the direct approach. We'll use the decimal as a mediator approach as a reference. So we have 1001110 binary equals 78 decimal, and that equals 116 octal, and that equals 4E hexadecimal. But let's see how we can directly convert a binary number to the octal and hexadecimal systems. As we learned before, every 3 binary bits can represent 1 octal digit, and every 4 binary bits can represent 1 hexadecimal digit. So starting from the radix point, let's divide the binary bits into sets of 3s, and we have a single 1 here, so we add 2 leading zeros. Let's make it neater. So we have 1001110, 3 bits, 3 bits, and 3 bits. By the way, the table I showed is pretty beneficial. It's included in the PDF of this video. Let's continue. These 3 bits are equivalent to 6. These 3 bits are equivalent to 1. And the same applies to these 3 bits. So here we have 1001110 binary is equivalent to 116 octal. That's very simple and direct, right? Let's see how it is with the hexadecimal system. The same principle applies, but we have 4 bits here. Starting from the radix point, we have 1110 for the first digit. For the second digit, we add the leading 0, so we have 0100. The first set is equivalent to E, and the second set is equivalent to 4. So that's equivalent to 4E in the hexadecimal system. And if we compare our result here, it matches the result from the generic approach, so our answers are proven to be correct. And this direct approach, by the way, is bidirectional. What I mean by that is we can represent a single digit in the octal system using 3 binary bits and each hexadecimal digit by 4 binary bits. Let's apply that to our example. Let's do the opposite. Let's convert our octal result here, which is 116, to the binary system. 6 is represented by 110, 1 is represented by 001, and the same applies to the other one. Let's put the sets together. So here we have 001, 001, 110. And you have to bear in mind that even the leading zeros must be represented here if a digit comes in the middle. Let's see what would happen if we ignore them. The result will be 11110, which is completely different. So bear in mind that we always have to pay attention to the zeros. So our result here matches the original number in binary. So our answer is definitely correct. And let's see how that plays out for the hexadecimal system. For E is represented by 1110. And 4 is represented by 0100. Let's put them together. We have 1001110 in the hexadecimal system. That matches our original number. So bingo. Let's see another example here. Convert 11000 11.11001 in binary to the octal and hexadecimal systems. Feel free to pause the video and try to solve it on your own. We'll use the direct approach here. Let's lay the bits out. So we have 110011.11001. We always start from the radix point to divide the bit sets. So since we're converting to octal, we need to separate every 3 bits together. So here we have 011, 100, and then 001, leading zeros here. And then on the right side, we have 110, 010, and trailing 0 here. All right, let's convert. This is equivalent to 3, this is equivalent to 4, and this is equivalent to 1. And on the other side, this is equivalent to 6, and this is equivalent to 2. So in other words, 110011.11001 binary is equivalent to 143.62 in the octal system. Now it's the hexadecimal system's turn. We divide the bits to 4 bit sets, and as always we start from the radix point. So here we have 0011, 0110, and on the other side we have 1100, 1 and 3 trailing zeros. Alright, so this is equivalent to 3, this is equivalent to 6, and this is equivalent to 12, which is equivalent to C in the hexadecimal, and the last one here is equivalent to 8. Alright, let's put them together. We get 63.C8 in the hexadecimal. Now, let's see an interesting example that is a little bit different. The example says convert 75.F hexadecimal to the octal system. Feel free to pause the video and try it on your own. According to our generic approach, we have to convert the hexadecimal number to the decimal number, and then the result in the decimal system to the octal system. But here we have the binary system, so we can use it as a mediator, right? Because converting the hexadecimal number to the binary system is much easier than converting it to the decimal number. So let's convert it. We have 75.F. F is 1111, and then we get the radix point on place, and then 5 is 0101, and remember it's always 4 digits because we're in hexadecimal system, and the 7 basically is 0111. So that's it. We've got our binary number here. So we did the first step. We converted the number to the binary system, and then from binary, we convert it to the octal system. So here we divide two sets of 3 bits. So here we have 101, 110, 001, and on the other side we have 111, 1 and 2 trailing zeros. This one is equivalent to 5, this is to 6, and this part is to 1, and the other side 7 and 4. So ladies and gentlemen, in short, 75.f in the hexadecimal system is equivalent to 165.74 in the octal system. If we use the decimal system as a mediator, it would have taken us much longer than this. Now let's move on to the last conversion category, which is conversion between other systems. As I mentioned earlier, any number can be converted from a number system to another by using the decimal system as a mediator. But the mediator does not need to be the decimal system. It could be the binary system, as we saw earlier, or it could be a base 5 system. For example, let's say we want to convert a number from a system where the base is 25 to a system where the base is 125. 5 to the second equals 25, and 5 to the third equals 125. So it's ideal to use a system with a radix 5 as a mediator. Conversion between other systems, this is not our main focus, but I will go over an example. Our example says convert 432.1 in a base 5 system to the octal system. As we know, the decimal system is the mediator here. So we'll convert the number to the decimal system, and then we'll convert the result into the octal system. Let's start with the conversion to the decimal system. 432.1 in base 5 system equals 4 times 5 to the second plus 3 times 5 to the first plus 2 times 5 to the power 0 plus 1 times 5 to the power of minus 1, and that equals 100 plus 15 plus 2 plus 1 over 5, and that equals 117.2 in the decimal system. Alright, now we've got the first step done. Let's move on to the second step. We have 117.2 in the decimal system that needs to be converted to the octal system. Here we have two parts, the whole part and the fractional part. The whole part here is the quotient and the remainder columns, and the product and the whole part columns for the fractional part. Let's start with the whole part. 117 divided by 8 equals 14 as an integer, 5 as a remainder. So the quotient gets 14 and the remainder gets 5. 14 doesn't equal 0, so we continue. 14 divided by 8 means 1 as an integer and 6 as a remainder. So here we have 1, 6, and we continue. 1 divided by 8 equals 0 integer and 1 as a remainder. So we have reached 0 here, and in the remainder we have 1. The LSB is 5, and that means 117 decimal is equivalent to 165 in the octal system. And then let's move on to the fractional part, 0.2. 0.2 times 8 equals 1.6. We get 0.6 under the product column and 1 under the whole part column. And then we continue. 0.6 times 8, that's equivalent to 4.8. So we have 0.8 in the product column, 4 in the whole part column, and then we continue. 0.8 times 8, that's 6.4. 0.4 goes to the product column and 6 goes to the whole part column. Then we continue. 0.4 times 8, that is 3.2. 0.2 goes to the product column and 3 goes to the whole part column. And let's keep it at 4-bit accuracy because we're not going to reach 0 anytime soon. So 0.2 in decimal is equivalent to 0.1463 in the octal system. Let's put both parts together. 117.2 in decimal is equivalent to 165.1463 in the octal system. And that is equivalent to 432.1 in a numbering system with the base 5. I'll leave you with some practice examples to practice on your own. The first is 1100111011.11111001 binary in the octal and the hexadecimal system. The second one B is 11ff.c hexadecimal in the octal system. The third one C 757.7 octal in the hexadecimal system. And the answers for those questions are in the PDF in the description of this video. Thank you so much for watching, and see you in the next video.